Hi, my name is Victoria Carmack. Today I'm going to tell you about the periodic table. The periodic table is a map of all the elements which compose all of life. So in a way, it's a map of life itself. Before we get into how to read this map, I want to give you a brief history as how it came to be organized the way that it is today. Although today we know that there's about 118 elements, back when Mendeleev was first studying all these, there was only about 60 known elements. Originally, the elements were also organized by atomic mass rather than the atomic number that they are today. They were just listed pretty much in a smallest to largest list format, and that's how they realized it. When Mendeleev was studying and interacting and all these different elements, he realized that they exhibited similar traits and characteristics periodically, about every 7 elements. Although now we know that it's every 8, at the time they were only studying elements that were reactive. So the non-reactive noble gases were not studied. While setting it up with the periodic law in mind, Mendeleev was then able to predict elements that had yet to be existed or discovered, and what characteristics and traits that these elements would have. So much so that when a French scientist discovered one of these elements and published saying that it had different characteristics than what Mendeleev had predicted, Mendeleev then published saying that the French scientist was wrong and why he was wrong. The kicker being of it all is that the French scientist was wrong and Mendeleev was right. Now that we've talked about how and why the periodic table was organized the way that it was, let's talk about how to translate the periodic table and use it like a map that it is. Starting with what all those numbers and letters mean. The top number is the atomic number. The atomic number tells you the number of protons that are in an element. It can be used without, and it's always the same. You change the number of protons, you change elements. The middle part right here is its symbol. It has either 1 or 2 different letters on there, and if it has 2, it's always a capital letter followed by a lowercase. The number right here is its atomic mass. The atomic mass is typically a decimal number. If it's not a decimal number, it's normally within parentheses. The decimal number is because it is an averaged amount from the atomic mass. To figure out the mass of an element, it's actually the protons plus the neutrons. The ones that are in parentheses, it's the most stable form of it. It doesn't last very long, typically. And finally, the name. The funny part of the names is they actually have to follow a set little guideline for it. The names either have to be based on a mythological creature like titanium, or a character, or a mineral or substance with similar substance or a property of an element like silver and gold or colors. It can also be named after a scientist like Einsteinium and Mendeleevium, or it can be named after a place like Germanium. Alright, so now let's talk about what the numbers on the top and the side mean. These numbers on the side are considered to be the period number. The period number actually tells you which orbital or electron shell it is. So all the ones on the first one, which is just hydrogen and helium, are only going to have 1 valence electron shell, while the second is going to have 2, where it goes into the second shell, like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and so on and so forth. It goes down. Now the numbers across are its group numbers, and you can see it goes 1, 2, 3, 4, 5, 6, all the way through 18. Okay? These two will tell you how many valence electrons. Now it gets a little bit different when you get into these, which are the transition metals. They kind of follow their own set of rules and they don't follow anybody else's, so they don't really quite apply. But if you were to go over to here and you drop the 1, it still works. So it has 3 valence electrons for the 13 and 4 valence electrons here. 5, 6, 7, and 8, which is actually none because it has a full shell. The periodic table is divided mainly into 3 large groups. It's your metals, which are all these blue ones, as well as the orange and the pink. They're a little bit different, but they are still metals. And then you have your metalloids, which are all these green ones. It also somewhat includes astatine and tennessine. It's just still debated. They both are still very unstable, so they don't really know if it's going to be a non-metal or a metalloid. And then you have your non-metals, which are not necessarily gases, but for the most part, they're gases. Each one of these groups have its own special set of characteristics. Your metals are going to be shiny solids, mostly. They're ductile, malleable, and good conductors. They have high melting points, and for them all but mercury, it's going to be solid at room temperature. Mercury is actually a liquid at room temperature. Then your non-metals are going to have, they're not especially shiny or ductile, and they're often poor conductors. They have a low melting point. Again, a lot of those are gases. Your metalloids are semiconductors. They have characteristics of both metals and non-metals, and they're just kind of stuck somewhere in between. There is actually a dividing line, which is purple here, that divides the metals from the non-metals. Around that, you can see that the metalloids sit around it, except for a few different separations for it, like the one noble gas and the couple that you don't know, and aluminum, which you all know is a metal. It's easy to set up to see where it is because it's a staircase that starts over here on the side of boron, and it just walks down like a staircase. And so if you're trying to figure out which metals is not, you start your staircase over here, go down, over, down, over, down, over, down, over, down, over, until you get to the end. Right? So within these metals, non-metals, and metalloids, there are several other smaller groups within it. You have your first row, which is your alkali metals. Your alkali metals are very reactive. They only have one valence electron, which makes them super reactive. They are malleable, ductile, really good conductors. The most reactive of the two are going to be francium and cesium. These can also explode when you expose them to water. The alkaline earth metals are very similar to the alkali metals, except for they are not quite so reactive. So within the middle part right here is your transition metals. Your transition metals go from 3 to 12. These have most of your everyday metals that you are using around for things like jewelry. You have nickel, copper, palladium, silver, platinum, gold, tungsten, zirconium, titanium, chromium, things you see all the time, iron, cobalt. All this stuff is what you use most of the time. The transition metals do have a different variety. They don't follow the same real rule of how many valence electrons they have, because the valence electrons can jump between orbitals or shells. Within the transition metals is what's considered to be the inner transition metals, which are your lanthanides and actinides. They're named after the first element that shows up into them, the lanthanum and actinum. So your lanthanides are all these orange ones, and your lanthanides are, they're silverly white color, mostly metals that tarnish when they're exposed to air, so they most of the time have to be suspended within something else. They're very reactive, they have a high melting point, and they're strong reducing agents. Now the lanthanides and actinides are so similar that they're very difficult to separate within normal circumstances. Your actinides, on the other hand, are all radioactive. They are very dense metals, and they have distinct structures and combine a lot with the non-metals. So outside of your metal groups, you have a couple non-metal groups. And again, the adenine and the tennessine may or may not be a metalloid, but right now they're deemed as non-metals. You have your halogens, which is group 17, your fluorine, chlorine, bromine, iodine, adenine, and tennessine. All of those are your halogens. Your halogens are extremely reactive, especially fluorine and chlorine, they form the most compounds with almost all the elements. Then after this is your noble gases. Your noble gases have a full valence shell, so they really don't react. They don't really feel to. The way I always think about with valence electrons is it's kind of like getting a collection. So over here they have one of the collections, so they're kind of really pretty much easy, like it doesn't matter, you can take it. But over here they're like, man, I only need one more. Just give me your thing, I need one more. But here the noble gases have all of them, so they really don't need any more. So they're just not reactive. They have no reason to react. They already have that full outer shell. After watching this video, you should have a basic understanding of as to how the periodic table came about and how it became organized in that way. You should be able to identify the atomic number, atomic mass, chemical symbol, and elemental name, and as well as what they represent. as well as the period table, the group numbers and what they represent, and all the groups within the periodic table and what they mean for you as to figuring it out. You should be able to use the periodic table as the map that it truly is.